Okay.
Okay, so we have our gas, right? I started this earlier. We got a gas in a container, right? Temperature, pressure. Okay, I'm gonna compress the gas. I'm gonna push on the gas, right? And compress it. And so what's gonna happen when you do that? What do you think? The volume's gonna decrease. The pressure increase. Probably the temperature will go up too, right? Does everybody seem good? Yeah, molecules are gonna move faster. Now that arrow is showing me where I'm moving it, but in order to compress it, in order to compress it, what do I gotta do? I gotta apply a force through a distance. What is that quantity? Work, I gotta do work, right? I gotta do work on the gas. So in order to compress a gas, I gotta do work. So let's see what that looks like mathematically. We'll come back to our simulator in a little bit. So if I got my gas here, so this would be a movable piston. This is like that. It was on the side. I'm gonna do it from the top. I'm gonna push down on the gas, right? So I'm gonna apply a force F down. All right, it's got a cross-sectional area A. I'm gonna change the volume here. So this is V naught, V final. I'm gonna get a delta V, V final minus V naught, right? And you see we have all the gas molecules in here. Okay, so I'm gonna do work on the gas. Work is what? Anybody remember the formula for work? Integral of
force distance.
F dx, right? Okay, we're gonna start with the easy case, then we'll put the integral in. So if we didn't have a variable force, what would it be? If the force is constant, then what is my work? I can put on the integral.
Force times distance.
Force times distance, right?
Yep.
That's the idea. Okay? Now, we're going to use that idea on this particular scenario, right? So I'm going to apply a force on the gas. But we usually don't write force when I do gases, I use pressure. So I have to write not F, but P times A, right? So this is the force I apply, the pressure, right, over the area of the object. Now I want to get the work I'm doing, right? That's going to be P times A, and the distance, well, the distance would be Y final minus Y initial, or delta Y. Right? Does that make sense to everybody?
What is A?
A is the cross-sectional area of my lid that I'm pushing down. It's the size of the piston. Now, we got to think, okay, delta Y, what is the sign of delta Y here? Y final minus Y initial, what's that going to be in this case? It's going to be negative. But I'm doing work on the gas, so I actually got to put another negative because I want to do work on the gas. So even though the volume, the area is changing, I'm putting work in. So actually I need a minus in this case because I'm compressing the gas. Does that make sense? And now it's A times delta Y. That's the area of the cylinder times the height change. That's going to give me delta V. Right, so that's going to be the work I do on the gas when I compress it. Pressure times the volume change. Yes?
Is that still an integral though? If it's
No, I haven't done the integral. Well, we're going to put the integral in just a minute. It's going to look almost the same with an integral. Right? And you can check the units, make sure they work out. What are the units for pressure? Anybody remember? Pascals, and volume is meters cubed, right? That's a bad M. But what can we write pascals as? Pascals I can write as newtons per meters squared, right? Force per area. So if I take a Pascal times a meter cubed, what do we get? Pascal times meters cubed. Well, that's newtons per meter squared times meters cubed. What cancels?
Meters.
Meter squared, leaving me 1 meter.
Newtons per meter.
Newton meters, Newton times meter, which
Force.
is
Force.
joules. So the units really work out. It's always good to know your units, right guys? Okay, so the units work. Now, what's the integral form look like? So that's the integral. This is if you have constant pressure, you can use this one. Otherwise, if the pressure is changing, you have to use that. Okay. Make sense to everybody? So I can do work on a gas, right? And I'll change its temperature, I'll change its pressure by changing the volume, and how much work I do is this integral. Okay. This is interesting. Because a lot of times when we talk about gases, we talk about PV diagrams. And this result isn't just in a gas. This is true for any system. I'm just going to use an ideal gas as our model because it's the easiest. But this is true for solids, liquids, non-ideal gas, a plasma, whatever. This is how you calculate the work. Okay? Does that make sense? All right. So let's say we start here on, and we're going to make an ideal gas for simplicity. We start here on this PV diagram. So I have initial pressure and initial volume, and I decrease the volume. I push on the gas with constant pressure, and I go over to here. All right, so this is, the pressure stays the same. This is the volume. So if I want to calculate the work, what does that mean on that graph? It's the integral of P dV, which is what? What's the integral of a graph? The area. Mary saved you guys. Right? It's the area under the curve. So this area here, that is the amount of work done. Right? Does that make sense to you guys? You with me? Okay. Let's try another, see if we get another concept before we start doing some numbers and calculations. Let's say this is my PV diagram. Here's my P and V. And I'm going to start here and go here. So this is P naught, V naught, T final, V final. Okay? And let's say we go from here to here on this PV diagram. Now keep in mind, ideal gas law. Anybody remember ideal gas law?
PV equals nRT.
PV equals nRT or nKT, right? It doesn't matter. So if the number of molecules, the number of moles are fixed, then if I know P and V, what else do I know?
R.
Well, R is a constant.
T.
So that's not going to change. I know T. So every point on this diagram, there's a PV, but there's also a T. If we keep N fixed, right? Does that make sense to everybody? So this has a certain pressure and volume temperature. This has a certain pressure, volume, and temperature. Let's say I go, to get from here to here on this PV diagram, let's say first I compress the gas like this, and then I raise the pressure like that. That should have been straight. Okay? So I'm going this way. All right? So I could do that. I could press the gas, then I raise the pressure.
Could you do both?
I could. I could have a path that looks like this. Right? I could do both simultaneously. That's what I was actually doing in the simulator. Or I could do something different altogether. Right? I could do something like, oh, it's already purple. I already got purple. Let's try a green. What do you think? I could go this way and then over here. Right? Now, in each of these scenarios, I have the same pressure, volume, and temperature to start and the end. But what's different for each one? I do different amounts of work. Right? Because work is what? Okay. That's the area. Area under the curve, right? It's the area. So this is a much smaller area than that one. Right? Does it even make sense? And this way is in between them. So the path you take through pressure and volume will determine how much work you have to do to move the gas from one location to another in the PV diagram. Okay? Does that make sense? All right, let's try some examples. What do you say? Matthew, you good with that?
Yeah.
I wasn't sure. You look very stoic back there.
I'm just tired.
It's tired. You had too much fun in the cold, huh? All right, let's pull up the book and look at some examples of this. Okay. Oh, we're just gonna start off with a hard one. Who likes that? Not, it's a blue. It's not hard. It's not red. It's a blue problem. Try to get this projector. Okay. Are we ready? Who's excited?
Yeah.
Thank you. Somebody excited. Okay. An ideal gas is taken through a quasi-static process described by P equals alpha V squared, where alpha is 5 atms per meters cubed, as shown in the figure. The gas is expanded to twice its original volume of 1 meter cubed. How much work is done on the gas expanding? Gas is expanding in this process. So that's your process. You're going from here to here, 1 meter cubed to 2 meter cubed, following this curve, which is given by this formula. How much work? All right. Ideas, thoughts, concerns.
I think we just integrate.
Okay, we just integrate. What do we integrate? What's our formula? We just wrote it. Work equals what?
B.
The negative integral of d dv.
dV.
Mm-hmm.
Okay. All right. So, Sarah, what's P? What am I integrating?
No, that's the.
Look at the first sentence. First sentence.
5.
I'm not integrating. Well, don't put in numbers. I'm integrating what? Danny, what am I integrating?
The alpha v squared.
Alpha v squared. That's P. P equals alpha v squared. So I got minus alpha v squared dv. Right? Does that make sense? Okay. Now what? Oh, what are my integration limits?
From 1 to 2.
Yeah. V naught v final. V naught equals 1 meter cubed. V final equals 2 meter cubed. Right?
Yep.
Okay. What's my next step? Jared.
Take integral.
Okay. What's the integral? V squared dv. Alpha's a constant. What I can do with the alpha?
Take it out.
Take it out. The work equals
Negative alpha. Integral.
negative alpha. I need the integral of v squared dv. So who remembers integrals?
1/3 d
1/3 v to the cubed. Good. V. Right? Does that make sense, everybody? It's not too bad, right? So minus. I think we're gonna have some unit issues, maybe. Because what do we have for alpha? Minus alpha is what? 5 ATMs per meters to the what? 6. Okay. Times 1/3 times V final cubed, which is what?
8
2
divided by
meters
3.
cubed, right? Minus V naught, which is 1 meter cubed. Right? Everybody see what I did there? I put it in the units so I can keep track of things. Okay, so what do we get? We get minus 5/3. That's the number. And then what's this number give me?
8.
8 minus
1.
1 is 7, right? Yes.
Those are meters cubed, right?
Oh yeah, meters cubed. Thank you. You're very excellent. I was testing you. Good job. Meters cubed. So that gives me a 7, right?
Yep.
And then what am I left with in terms of units? I got an ATM. I got meters to the what here? Meters cubed is, nope, 9.
Meters 9.
Divided by meters to the 6. So I get a minus 5 times 7, what's that? 35, right? 35 thirds. The units are ATM meters cubed. Guessing this is going to be in joules, so that means I got to do what? Unless you have ATM meters cubed, that's a weird energy unit. I mean, those are energies, but usually we want joules, so I got to convert what? What are ATMs?
Pascal.
Machines that give you
Okay, machines give you money, and you got to convert them into energy. No, it's atmospheres, and I got to convert atmospheres to pascals. Right? Does that make sense, to everybody? Now, I don't know the conversion offhand, but
Come on, come on.
I know.
Should be right there.
I know. What, Mary?
Pascals equal newtons over meters squared, right?
Yes.
So, okay,
Yep. That's because it's the SI unit.
that's why we're going to.
There it is. So, I looked it up earlier today for the first class. 1 atmosphere is 101,325. 101,325 pascals. Okay. So I just gotta convert atmosphere. So I just gotta put in that 101,325. So the word equals minus 35 over 3 times, instead of an atmosphere, I have 101,325 pascals times meters cubed, which gives me joules. So some guy a calculator can do that for us? So that wasn't too bad once I looked up the conversion, right? They probably do it in scientific notation, I bet, because it's going to be a big number. It's going to be a good size number. What is it?
1182125.
1182 what?
125.
Joule, right?
Yeah.
182. That's 1, 2, 3, 4, 5, 6. 1.18 roughly. 6 joules. 1.1. That's what I'm guessing they're going to put. Megajoules. Oh yeah, that's a megajoule, right? 10 to the 6 is what? Mega. So we did it. Nice job, all of you. Okay, let's try another one. What do you say?
What's that? Us times.
What?
We keep the negative sign, Dr. Browning?
Yes. Yeah. Because what's happening? The gas is expanding. So actually, the gas is in. So this is interesting. So we're not actually doing work on the gas. It's called the work on the gas, but actually, what's happening? The gas is doing work on the environment because it's expanding. So we have two works here, and you have to be careful. There's the work done on the gas, which is this formula. This is the work done on the gas. The work done by the gas is equal to the integral of PdV. So these are equal and opposite of each other. And we always calculate the work done on the gas, because that's what we're going to use in the next equation, the next big equation.
Okay.
But this makes sense because of one of Newton's laws. What law of Newton's relates these two quantities?
Third law.
Third law, equal and opposite, right?
Yep.
If I apply a force to the gas, what's the gas do? Applies a force back to me
And that no
in
energy.
the other direction.
And also that no energy is destroyed, but
Right, yeah. Right, exactly.
conservation of energy.
How come
So-
they keep an M like that?
What was that?
For the answer, they keep the M.
Yeah, that's mega.
Oh.
That's the times 10 to the 6.
Mm.
Okay, let's try another one. This one has an answer, so we'll try it. This one we're going to have to do a little more, I think, conversion of area maybe, or not. Let's see. This one might take a little thinking as well. But you got to do a lot of thinking in these problems, so that's why I like these problems, even though it's a black problem. Okay. An ideal gas is enclosed in a cylinder with a movable piston on top of it. Kind of like that picture there, right? So we can use this picture. So I'm going to erase this, because that's a good picture to start with. Okay, there's my movable piston, right? And it's got an area, right? The piston has a mass of 8,000 grams and an area of 5 centimeters cubed. So the cross-sectional area here is 5 centimeters squared, right? And it's free to slide up and down. Keeping the pressure of the gas constant, that seems important, like a key word, doesn't it? Yep. So I'm going to underline that. How much work is done on the gas? So we got to calculate work as the temperature of 2 moles of the gas is raised from 20 to 300. I think I underlined everything important, right? So I don't know the mass of the piston, which is what? 8,000 grams? But I don't want the mass, I want what? Matthew, what do I want?
I don't know what you want back.
Oh, but you were putting your hand up because you were going to answer, right?
No.
Okay, question.
Is the fact that it's free to slide up and down important? Like in the question,
Yeah.
it's free to slide up and down. Does that matter? Does that mean like at some point we're gonna have to add friction into these if it's not free to do that?
Yeah. Nice. I love you looking ahead. Mary,
Wait, what question did you ask? What do we need for the piston?
what do I need? Because I have mass, but in my formula I need, because this mass is sitting here, right? This is the mass, right? But I don't need mass, I need the pressure. What's creating the pressure?
Mhm.
The weight. So I need to calculate the weight and then get the pressure. Right? How do I calculate weight? Jared.
You have to use gravity.
Gravity. So the weight, I'll make it a cursive W so don't get confused with work. Or straight W. Weight is what?
Mass of gravity.
That's gravity. And then pressure would be what? Force per area, or mg over A. Does that make sense to you guys? The only thing is, they gave me mass in grams, so I gotta do what? Convert. Which is what? 8. That wasn't too bad of a conversion, was it? We like that one. Okay. Alright. Let's draw a PV diagram of this scenario so we can kind of visualize what kind of curve we're talking about. Last one was an exponential curve. Okay, what kind of curve is this? So if I start at 1 pressure, let's say I start here,
Pressure's gonna be constant, right?
pressure's constant. What does that mean?
Straight line.
I'm gonna go from here. Oh, now, but what? Ooh, I'm compressing the gas, right? So actually, I'm gonna start here and go over to here. Right? Does that make sense? Because I'm pushing the gas down. Because the temperature's going up. Right? So I'm going from a P naught V naught to a P final V final. Also, what corresponds to every point on this PV diagram? A PV, but there's also a 10, right? So I also have a T naught, T final, right? Does that make sense? And what relates these quantities? P, V, and T.
Ideal gas law.
Ideal gas law. PV equals RT. Okay, what kind of curve is that? If I look at that graph. Constant pressure. Horizontal line. That means I just got to do what?
Compute the area.
Do the area. Right? To get the work. Does that make sense? Okay. We can do that, right? Work equals what? Minus P delta V. Okay, what's P?
mg over a.
Mg over A. Nice, man. Minus Mg over A. That's P. Okay, delta V. What's that going to be? Oh, crap. They didn't give me V. What did they give me?
Temperature in moles.
Okay. Well, are they related?
Yeah.
Yeah. I could solve this for V in terms of T, can't I? So if I do that, what do I get? V equals nRT over P. Right? So I can calculate this, can't I? V final would be what? nRT final over P. And what's V initial? nRT initial over
P initial.
P, right? Because P is constant. The P final is equal to P naught, isn't it?
Yeah.
I'm just going to call it P. Because it doesn't change. Okay, so we put in for that. So we get work equals minus mg over A times V final. That would be nRT final over P minus nRT initial over P. What can I factor out? Anybody? nRP. Minus mg over A. I really need a white screen. This is getting a little crazy. Not the history Okay. Now I can erase some stuff here. So minus mg over A, and I factored out a n r over p, and then what am I left with?
T final over T net.
Did you say over?
Or, yeah, I did, but subtracted, yeah.
Subtract. Right? Okay, so now we can start putting stuff in maybe, right? We know M, right? We know G, everybody remembers G, don't they? N is the number of moles, which I think they gave us, didn't they? What was it? 2? I forgot to write that down. Okay? R, gas constant. That should be something I'll give you on the test. But I think R, if I remember right, is it 134 or 314? That's what I thought. Joules per mole Kelvin, right? Oh, but they gave me that area in centimeters. Oh my god. And they didn't. But what? Look at this. This is kind of cool. What's pressure times area equal to?
Wait.
Yeah, pressure times area is equal to mg. So I could actually write this as minus mg/r divided by mg.
You can cancel.
I cancel. So I didn't have to convert that area anyways. And then T final minus T initial, that's just delta T, isn't it? So the work is minus N R delta T. So you said it was 2, is that right?
Yeah.
8.314. Now, here's a little trick. Normally we gotta do temperature in Kelvin, but it's a delta T, so guess what? We can stay in Celsius. Right? Because the 273 is gonna cancel if I convert to Kelvin. So you could convert to Kelvin. Everybody see what I'm saying? But then you're gonna have a plus 273 and a minus 273 and they'll disappear. So we can just do it in, and what were our T's? I don't remember.
300 minus 20.
300 minus 20. Thank you. All right, Mary's going to give us an answer.
It's negative 4,656.
4,656. Is that what you got? Jewel? Let's see if that is correct. Negative 466. Oh, it's 0.2, not 2.
Oh, sorry.
This is 0.2. Power 10. Right? You can see that? I know it's got writing all over it.
Yeah, 0.2 mole.
What is that? Oh, right there.
A day.
Okay, so we got it right. Just move the decimal point. Okay. This is the idea. Try one more. Just so we get it down really well.
Dr. Brown, a quick question.
Yeah.
You said that we usually have delta T, we use Celsius, right? Or is it the other way around?
So if you have a delta T, you can do Celsius.
What else do you use Celsius for? Nothing?
Yeah, I mean, it's only usable in a delta T. Like specific heat, that's delta T.
Celsius.
Right? This doesn't end up being a delta T. But if I just have a T,
You have to use Kelvin.
then I gotta do Kelvin. So like, we had a delta T in conduction, but we had a T to the 4th minus a T to the 4th in radiation. So that had to be in Kelvin. Right, does that make sense? It's only with the delta T. That's just too easy. Alright, that one's easy. You guys could do that, can't you? Determine the work done on the gas as it expands from I to F. Let's try it, since they give us an answer. Okay. So what's the work done on the gas that expands from I to F? Right? It's just what?
The area.
The area under the curve. So can you guys find the area under the curve there? That should be easy, right?
Can we break it down in sum?
Of course.
Like superposition?
Yeah, just add up the rectangles, right?
Yep.
You got a rectangle here,
Mm-hmm.
which is what? It's
4,
1 times
4.
4, so that's 4 times 10 to the 6, right? And this is a what? That's a 1, isn't it? No, that's a 2.
2.
That's a 2.
That's a 2 again.
2. What's this one?
Ooh, that's tricky. Maybe 2.
1/2 base times height. It's a triangle. Come on, it's not tricky.
Tricky.
Can't believe you said tricky. 1/2. What's the base? 1. What's the height?
2 times 10 to the 6.
From here to here, just that little triangle.
4.
4, right?
Yeah.
Which gives me what?
2.
2. So 4, 6, 8, 10, 12.
Quick question. Instead of doing all the formula that you did for a triangle, can we just say that it's half the other way we found? Like we found 4, right? Can we say that the other one is half?
Yeah, because it's be the same rectangle.
Yeah.
Yeah.
It would be simple.
Yeah. All right, 1/2. Everybody see how to do that? So the answer is -12. Right? Because it's. What if you go the other way? What's the answer?
Positive 12.
+12. Right? Because in the other direction. So. Times 10 to the 6. Right? Negative. Okay. All right. We're going to use this stuff. And we're going to do all kinds of things to gases. Expand them, contract them, and see how that process goes. And in the process, eventually we're going to build a theoretical engine. Right? Like your gas engine. What's your gas engine do? You guys drive a gas car? I drive an electric now. It's not cool. But what's a gas engine do? Who's got a gas car?
What do you mean, what's it do?
How's it work? How does the engine work?
Well, you got these pistons firing.
Yeah, and what's in the piston?
Yes.
Yeah, you pump in gas, right? But it turns it from gas into liquid gas into gas, right? And that causes the piston to expand. It does work. So we're going to see how we can take this and do useful work, make an engine.
We're gonna build a car.
Yeah, we're going to build a theoretical car.
Lord, it's boring.
Right? A theoretical car, a theoretical steam engine, a Stirling engine, a diesel engine, theoretically. I can't build one for real, but I can show you the mathematics how it works. Right? So we're eventually going to get to that, see how engines work. Okay? All right, I'll let you go early. Don't tell chemistry. Yeah, so we are in 17, and yeah, I think we're going to be in 17 all this week. Because there's a lot to do now that we.
Can I stop the recording?
Yes.